Okay. All right. So, hello guys. So anyway, we have been talking about, we spoke about orthogonality and orthonormality, and precisely what is a orthonormal basis, what is the meaning of an orthonormal basis. Okay, this has all got to do with how you try to, decompose complex matrices into simpler one and leverage their structure in solving different kinds of application problems. Okay. Now, it all started with basis of a vector space. You know what a basis of a vector space is. And it's a minimum spanning list that is also, a linearly independent set. Okay. And so this was the last bit of the lecture that we had last time, right? And any matrix or corresponding linear transformation is orthogonal if its inverse and the transpose are exactly the same. Okay. Now, what is orthonormal? Orthonormal is a set of vector, like one vector, one column vector, two column vectors, right? I mean, they are orthogonal to each other, which means their inner product is 0. And also, if you compute the length of each one of those vectors, the length of each one of those vectors should add up to 1. Okay, which means nothing but square root of, if it's x1, x2 all the way up to xn a column vector, then square root of x1 square plus x2 square all the way up to xn square should be equal to 1. Okay. So it's nice to have some orthonormal basis because then you are able to decompose the matrix into, nicer matrices. Okay, so one such example is, you can decompose a matrix or a linear transformation into 3 matrices. In this particular case, A is equal to P, D, P inverse, where D is a diagonal matrix that will contain your eigenvalues of A. Okay, and the matrix P, because you see on the right, the inverse of the matrix exists, right? So the matrix P has to be a full rank matrix. Now, what do you mean by a full rank matrix? A full rank matrix means its columns are linearly independent of each other. So you have a set of column vectors, okay, that come from your original matrix A, right? Now, in the original matrix structure, your column vectors may not be linearly independent. But if your matrix is a symmetric matrix, right, real and symmetric matrix, then you'll be able to decompose that matrix into this kind of a structure where P is an invertible matrix. Invertible means it has to be a full rank matrix, right? Okay, and its determinant is not equal to 0. And you know that in a matrix, if the determinant is not equal to 0, it means the matrix has to be full rank or its columns have to be linearly independent of each other, right? Okay. Now, in this particular case, if A is a real symmetric matrix, the columns are the eigenvectors. Eigenvectors of the matrix A. Now, why would a set of columns which are eigenvectors of a matrix A would be linearly independent of each other? It's because of a set of nice properties that we mentioned in the first class in the context of PCA, where we said that if a matrix is real and symmetric, its eigenvalues are real and distinct, right? Okay. Then the corresponding eigenvectors are actually orthogonal to each other and therefore are linearly independent. So we proved that orthogonality part, right? If you recall, we haven't said anything about the verification of the linear independence part that we will do today. Okay, but the condition is that your matrix or the linear transformation has to be real and symmetric. Okay, now on top of that, if your matrix is also an orthogonal matrix, then your transformations, this kind of matrix decomposition slightly changes, because if your transformation of the matrix is orthogonal, you know that your P inverse is nothing but P transpose. So what you are writing as PDP inverse can be rewritten as PDP transpose. Okay, and this kind of matrix decomposition has its own advantages. I showed you one example in the last class, right? Okay, that if you exponentiate a matrix to any order, right, on any power, then that exponential operation, by virtue of the matrix being real and symmetric, becomes really, really simple, because it all boils down to exponentiating the diagonal matrix, which is really easy, because when you exponentiate a diagonal matrix, you just exponentiate the individual elements of the diagonal matrix, which are just non-zero along the principal diagonal, and everything else is 0. Correct? Okay. Now, in the context of, we also spoke about orthogonal complement, right? And we said that if I have a vector space, and then the vector space may have two subspaces, one is one subspace, and then the other subspace is nothing but the orthogonal complement of that one, which means I have a set of vectors, right? And in another subspace, I have another set of vectors, and these two sets of vectors are orthogonal to each other, which means pairwise their inner products are 0, right? Then any vector space can be decomposed into one subspace and its orthogonal complement. Okay, and you can write that vector space as a direct sum of that subspace and its orthogonal complement. So what is a direct sum? This direct sum is nothing but you take the sum, algebraic sum of these two subspaces, the subspace and its orthogonal complement, and that will give you back the original vector space. And also the intersection of the subspace and its orthogonal complement is null. We showed that graphically by invoking the support vector machine example, right? I mean, when you begin support vector machine, there is no guarantee that you have a margin, right? So in the margin, on either side of the margin, you have a set of vectors, right? When you begin the classification process, there is no guarantee that these set of vectors are orthogonal to each other. But upon achieving 100% discrimination between the two classes, you have two sets of vectors which are perfectly aligned on either side of the margin. So there is practically no intersection between them and no region of confusion. So therefore, the probability of misclassifying sample from class 1 as class 2 and vice versa is 0. Okay. So if a support vector machine achieves this kind of 100% classification accuracy, then you can treat vectors lying on either side of the margin as vectors lying belonging to subspaces which are orthogonal to each other, right? And one subspace is an orthogonal complement of the other, and you take the direct sum of that, you get back the original vector space, and the intersection of the two subspaces is null, which is the margin. There is no vector which is supposed to lie in the margin, right? Okay, that's the founding principle of a support vector machine. Okay, all right. So with this, I mean, I think we are ready to talk about some other stuff, okay, which is, I mean, as I said, when we are speaking about principal component analysis, I said that I will give you an introduction to singular value decomposition as well, which is a near extension of a PCA, or you can think of PCA as a special case of a singular value decomposition on SVD. Okay, this has immense applications in many places, image processing, PageRank algorithm that Google uses, and lots of other places, right? Okay, all right. So let's begin with a clean slate. And by the way, if you notice that I have added a few more folders in the classwork. Okay, all right. And I'll be exporting the classwork as PNG files into a whiteboard folder that I have added. Okay. Couple of things I want to say before I begin the formal lecture. One is that from next assignment onwards, do not can you hear me? Hello?
Yes.
Yeah, okay, all right, okay. So from the next assignment onwards, do not upload your solution to the homework folder. Okay, so you will receive a detailed instruction from the teaching assistants as to how to link your own solutions to the assignment folders. Okay, all right. So that's number one. And number two, I mean, a lot of you have already submitted the assignment to the homework folder. I have gone through some of the solutions. I mean, what I notice is, and this is expected, I mean, you are just beginning and you are not familiar with the abstract way of thinking. I have not found your solutions to be elegant. They're right solutions, they're correct. I'm not saying they're wrong, okay, but they're not elegant. I mean, and so, I mean, just because I was hoping that I would just go through one of your solutions and then use it as a standard, template. But then I just looked at your solution and then I solved the problem myself. Okay, all right. And when I share the solution with you, you will know what I mean. Okay. Once again, your solutions are not incorrect. Okay, and you are going to get the full grades out of it, but try to, write elegant solutions. Okay, all right. And the second assignment onwards, all the assignments have to be typed, because if you write it on a piece of paper and upload, then there is no way I can check for plagiarism. So it has to be typed from second assignment onwards. Okay, all right. So, okay, so I think there are no more questions. And I think there was like a couple of questions after the end of the class last time, and they requested me to just go through the material that I covered in the last class, which I have done. Okay, all right. Yeah. LaTeX says, I mean, you can type it in Word and convert it to a PDF, but that's painful, right? So, just type it in LaTeX. The automatic rendering will be PDF, and just upload the PDF. All right. So, typically, what really happens is the following. So, what is a singular value decomposition? Any idea? Guys, any idea? Have you heard of singular value decomposition? I guess no. Have you heard of the page rank algorithm of Google? You use it every day, right? Yeah. So anyway, the page rank algorithm, the way it works is, it is supposed to show you the top ranked websites in the first couple of pages, right? And then based on your search string, the importance of the documents are, arranged in an ascending order. Okay. Now think about this. Each document has a representational value. In Google search, right? Each document has a representational value. And if you think of associating each document with some sort of a singular value, okay, there is one singular value which is a quantitative representation of what you are really searching for, right? And the magnitude of that singular value, it's arranged in an descending order, sorry. So the magnitude of the singular value, the web page which is most relevant to your search should have the maximum singular value. So what you are getting in the Google search is a spectrum of singular values arranged in a descending order. Okay, so the maximum value is at the top, and then as you go by page, the singular values decrease. Okay, so this is the way. Of course, Google has made many refinements to this particular type of an algorithm, but this is the standard way the page rank algorithm was written. In fact, the reason why it's called page rank algorithm, it's because one of the founders of Google, Larry Page, it was his PhD dissertation. Okay. All right. So the idea is, since we are talking about eigenvalues, invariably matrices or linear transformations will come into picture, right? Okay. So how? Now, what you have typically is an input data matrix where you have a number of documents and number of terms. So this kind of a matrix representation is known as a term document matrix. Okay. Now, what a singular value decomposition gives us is that this particular matrix, I'm talking about eigenvalues, right? Okay. So when I talk about a matrix, we think that eigenvalues of a matrix gives the matrix a lot of representational power, tells us a lot about matrices in general, right? Okay. But for square matrices, now typically when you look at an input data matrix, you don't expect the matrix to be square, which means your number of documents would be actually much larger than the number of terms or keywords, right? Okay. So this needs to be decomposed into a bunch of matrices. So if you are able to do that, just in the same way you decompose a symmetric matrix into three different matrices, right? P, D, and P inverse, right? Is there a way to decompose a non-square matrix, okay, into three different matrices? Turns out that there is, and that is the whole point of singular value decomposition, is that you decompose into three matrices. The leftmost matrix contains a singular vectors, which contains the number of documents and the number of concepts. Now, what is the concept? The concept is the strength of what you are actually searching, the latent information that is there in your search string. Okay, and this leftmost matrix is followed by another matrix which is known as the singular matrix, and this singular matrix is of the rank R. Now this rank R is nothing but the rank of the original matrix. Okay, and this singular matrix represents the singular values aligned along the principal diagonal of the matrix, okay, in descending order. So each one of these values, R1, R2, R3, each one of these values signify the strength of the concept. Okay, all right, and accordingly your documents are arranged. And then you have a right matrix, okay, where you keep the terms and the concepts. So as you can see, the number of documents are much, much larger than the number of terms, and the strength of each concept, the number of concepts are also larger than the number of terms. Okay, so if I give you an example, let's say you take data from Netflix, right? And so there are a number of people, lot of people. Okay, I am not using the whiteboard yet, guys, don't worry. Okay, when it's time to see the whiteboard, you will see the whiteboard. Okay, all right. So let's say I have a Netflix example. Okay, so all right, since you guys are forcing me to use the whiteboard, let's do that. Okay. Okay. All right. So here is the deal. I mean, let's say there is a Netflix example. There is one matrix, okay, and this is the matrix A, and this is nothing but it's a non-square matrix where M is the number of documents and N is the number of terms. Okay, and typically M is way bigger than N. Okay, so therefore you know that you are looking at a non-square matrix, and therefore you cannot directly compute the eigenvalues of this matrix. Okay, that's where the challenge comes from. Okay, and so what you do is you decompose this guy into three matrices. Okay, each one, these two guys, U and V, are actually orthogonal matrices. Okay, and this is what is called as a singular matrix. This is where you are going to store all of your singular values. Okay, so you can call this sigma 1, sigma 2, sigma r. So this guy is M by R. This guy is R by R. Okay, and this guy is N by R. I mean, V is an N by R matrix, so V transpose is R by N. So you get back, if you do this multiplication on the right, you will get back the matrix A. Okay, all right. Now, what I have here in this particular data matrix, input data matrix, is that there are a bunch of people who watch a lot of movies, right? And movies have genres, right? You have sci-fi, comics, fiction, documentary, and all that. I mean, there are different kinds, right? Okay. Now, these guys give ratings. So what you have is that, I mean, here along the columns, you will have movies. Okay, all right. And what you have here inside the input data matrix are ratings. So people have rated different kinds of movies. Now the question is, what you want to extract, the latent information that you actually want to extract from this, the latent information, is that which of the genres are more popular. Is sci-fi more popular than romantic movies? Is the genre of romantic movies more popular than comedy, and so on and so forth, right? So what we try to do from this sort of decomposition is that we try to learn some concepts. Not only we learn some concepts by the strength of concepts. And the strength of concepts are directly given by these singular values, sigma 1, sigma 2, all the way up to sigma r. The question is, how do we compute this? The computation is not straightforward because, as I said, your A matrix is a non-square matrix. So you cannot directly compute the eigenvalues, right? Okay. So how do we do this? Okay, there are a bunch of things that we need to actually figure out before we try to solve this problem. Okay. So at this point of time, I would like you to note down a few things, okay, because I can't write everything on the whiteboard. Is that the underlying principle in solving this kind of a problem is to know that what is a vector. You should know what a vector is. What is a vector space? What is a span? What is a basis, right? Because eventually you are going to decompose the non-square matrix A into orthogonal basis, okay? Because both U and V are orthogonal matrices or linear transformations, orthogonal linear transformations, right? You definitely would like these matrices to be linearly, the columns of these matrices to be linearly independent. You would need to understand the notions of eigenvalues and eigenvectors. Orthogonality is a very, very central concept in SVD, okay? And then we also need to talk about symmetric positive definite matrices or transformations, right? Dimensionality, so on and so forth. So there are some important results that we need to brush through before we actually can delve into how to solve this kind of singular value decomposition problems. Okay, guys, please note down. Okay, all right. So there are some very, very important results, and these are preliminaries, and we have discussed some of these preliminaries already. The first one is that orthogonal matrices or linear transformations preserve angles and lengths. Okay, so let me write this down here. Orthogonal matrices preserve length and angles. Which means, there is sort of an invariance here. Distortion is not allowed under orthogonal transformation, right? So if you recall, what is a transformation, orthogonal linear transformation? An orthogonal linear transformation is that I have a transformation from vector space V to vector space W, right? And I should be able to define an inner product, right? I would rather probably, what I should do is just to make things consistent. Okay. I'll just take V here, which belongs to the vector space capital V. So this kind of inner product is defined, right? Okay, all right. And what happens is that I should be looking at the inner product of this, okay? Because you're applying a transformation T onto V and you're producing W, right? Okay. So when I say orthogonal matrices or transformations preserve angles or lengths, what I need to show is that the inner product of TV and TW has to be exactly equal to the inner product of V and W. Because you should also know, right, that when you look at the norm of V, which is nothing but the length of the vector, right? It is nothing but the inner product of the vector with itself. Okay? All right. So this is nothing but the length. Right? Okay. So now what I can do here is the following. Is that we also know, we should also recall that when you have two inner product of two vectors, I can actually write it is in this manner, this fashion, right? Okay, all right. So the same thing I can do here, right? So what I can do is, by using the property of the inner product, right? I can write it this way, isn't it? Then, using the property of the transpose, this is why I like transposes, right? And I told you in the first class that, I mean, nobody should have the fascination of, taking the transpose of a matrix if it's not useful, okay? It's not just cutting one row and pasting it as a column, right? I mean, it must be having some usefulness. So you will see the usefulness here now. Now, what do you know about this T transpose T? You can speak. T is orthogonal, right? So therefore, this T transpose T, if I have an orthogonal matrix, T transpose T is nothing but the identity matrix, right? This is by definition, correct? Okay. So therefore, what I have is W transpose V, or in other words, VW. Correct? Right? Or in fact, this is WV, but inner products have a symmetry property, which is WV is nothing but VW. And so therefore, what this tells me is that orthogonal transformations under inner product, it will preserve your length. Okay, all right. Okay. What it also means is that if I replace this W with V, which means if I take the inner product of a linear transformation with itself, I can simply use this property. Okay, I can simply use this property, which is then I replace this W with V as well, right? So this is just VV. Now, what is this guy? This is nothing but the length of the transformed vector, right? And this is nothing but the length of the original vector, right? Okay, so what is TV, guys? What is TV? TV is nothing but, I mean, you have a vector V, right, which belongs to this vector space capital V. You apply a transformation on this, which means you are operating the vector V with a linear transformation, and what you are getting is TV. Now, where is this TV guy resides? Where does it stay? It stays in the vector space W, correct? So this T is nothing but a linear mapping from one vector V, which is in the vector space V, capital V, to another vector, right, which is in the vector space W. Okay, all right. So therefore, by virtue of this linear transformation, you are producing another vector, right? And so this is the length of that vector. Okay, this is the length of the vector under that orthogonal transformation. And this is the original length of the vector. What do you see? That these two lengths are exactly equal to each other. Okay, that is why orthogonal linear transformations are length preserving. Okay, so you are not distorting the vectors, because typically when you have when you look at the eigenvalue eigenvector situation, you, based on your scaling factor, you can actually distort the vector, right? You can shrink it, you can expand it. In this case, you are doing nothing. You are keeping the original length, right? Okay. And then there is the other thing, which is the angle between TV and TW is nothing but the angle between the V and W. Okay, do you see this? Okay, so let me just first export this out, and then I will erase this. Okay, so now what I'll do is, let me just remember this. Okay, all right. So now, I mean, it's pretty simple to see, right? I mean, if you look at the inner product, TV and TW, it's nothing but, your definition of inner product or dot product. This is nothing but the length of the individual vectors and cosine of the angle between them, isn't it? Similarly, if you look at the inner product of V and W, it is nothing but the length of V times the length of W times cosine of the inner product, or the cosine of the angle between V and W. Now, by virtue of the previous property that we have shown, we know that under orthogonality, the lengths are preserved, right? So that means these two guys are equal to each other, right? So which means that if TV TW is equal to VW, then these two angles also must be equal to each other, right? Okay, so that means the angle between the vectors V and W residing in the vector spaces capital V and capital W, and under the orthogonal linear transformation, the angle between TV and TW, they are exactly the same. Okay, and that's the reason this is known as angle preserving as well. Okay, all right. So orthogonal linear transformations, a nice property that is used in singular value decomposition, is that they are both length preserving and angle preserving. Okay, all right. Okay. Now, the next property that we need to know.
Excuse me, sir.
Yes, yes, yes.
Sir, the small w here is part of the capital V vector space, right?
No, the W vector space. But by virtue of the linear transformation, you are mapping elements from vector space V to vector space W, right? So this small w is in the vector space W.
So still we can apply the same linear transformation on it. Won't the dimension?
Right, no. See, it's an image, right? So I mean, just think about it as from a function space point of view. You have a domain and you have a range. So when you apply a function f, it takes a value x from the domain and it maps it to a value in the range, right? Now, your domain and range could be exactly same, but that is not a necessity. I mean, you can have the domain and the range exactly equal, but you can also have domain and the range different from each other. Okay.
Right. So here they are different, right? Capital V and capital W are different.
Exactly.
So still we can apply the transformation on the vectors from V also and W also, the same transformation.
Yes, of course. Yeah. Okay. Right. Okay. So the next one is that the next property that we need to talk about is that the eigenvalues of an SPD are real and are positive. Okay, what is an SPD? SPD is nothing but symmetric and positive definite. Okay, now we don't know what an SVD is, correct? So let's talk about it. I mean, let's talk about some geometry. Okay, all right. So let's think about this from I mean, you are familiar with parabolas, right? A general second order quadratic form. So a very essential term. I don't know whether you have heard of this, but that's okay, right? So in general, quadratic form, it looks like a quadratic, right? I mean, you think about this. I mean, if I write this, it will immediately come back to you. Let's look at a standard quadratic form. Would you agree that this is a quadratic form, right? Yeah. So in general, it's a function of more than one variable. Okay. Now, I'm not sure whether you are exposed to finding out, I mean, solving optimization problems for functions with more than one variable. I'm assuming you have done something of that sort in your previous calculus classes. Okay. All right. But let's assume that you don't. Okay. But you know that this represents a parabola, right? Represents a parabola. Okay. Now, this parabola has some special properties based on the values of the coefficients, right? So let's assume that this A guy is greater than 0. Okay, all right. Now, if this A guy is greater than 0, so now this parabola could be face down or could be face up. So you can think of this as a bowl, right? I mean, like a soup bowl, right? Now, if it's face down, it means that, I mean, you have a minima somewhere, right? And everything from that minima is going up. Okay, so A greater than 0, and there is another condition that ensures that you have such a parabola, okay, with a minima guaranteed local minima. Okay, all right, and that's also because this type of functions or this type of functional forms are convex, but let's not worry about convexity right now. Okay, all right, but the geometry is something like this, right? Okay, so you have a minima. If you recall, I told you that one of the reasons why people like linear algebra is because the geometric interpretations in higher dimensions are beautifully represented using matrices and linear transformations. And that's the whole point of bringing this up. But I mean, a very simple thing we can do, right? If you look at this, just observe carefully, guys. Okay. All right. So what I have done is I have written a row vector on the left. I have written a column vector on the right. And in the middle, I'll write a 2x2 linear transformation or a matrix. Okay. Can you tell me what are the elements of this matrix? You can speak. No idea?
A, B, B, and C.
Excellent. Excellent. Who was that? Who is that? Because I don't see you. No. Hello. Can you speak up your name?
Sir, Rahul Saxena.
Rahul Saxena. Rahul. Very good. Okay. Also, Rahul, can you tell me in this 2x2 linear transformation or the matrix, what is the determinant of this guy? It's easy, right? It's a 2x2. What is the determinant of this?
Sir, AC minus B square.
Yes, very good. Let me now write this. So you know column vector notation as an X. So if this is a column vector X, this has to be X transpose. And let's call this matrix A. Okay. So this parabolic expression or a quadratic form can be written as, I can represent this as X transpose A X. Okay, all right. And this is conveniently known as a quadratic form of multivariate functions. Okay, so what you see here is, and you can do this for any amount of any number of variables. Okay, all right. But the question is, what I want to ask is that if I know some properties of this guy A, using those properties, can I say something about the minima of the function or the quadratic form that I have here? Okay, so geometrically, when you go to higher dimensions, you know, in 2 dimensions, when it's a parabola, it's easy to represent it in a 2-dimensional plane. You can draw. But if I give you a function like ax x1 square plus 2b x1 x2 plus 2c x1 x3 plus 2d x1 x4 blah blah, a function, right? But typically your column vector is no longer a 2 by 1, and it could be an n by 1, right? Okay, so there it is impossible to represent this graphically, right? So, but if you really want to know for certain expression what would be the minima or maxima, right? Then what are you going to do? You would have to have some representation, right? Your matrices and transformations actually give you that representation. Okay, so therefore, so this is clear, right? I mean, how a quadratic form can be represented in terms of a matrix, and this can be easily scaled up. Okay, so the question is, what special properties does this A guy have to have? Okay, all right. Now, I mean, forget the matrices. I mean, let's look at the conditions for minima for this particular guy. Okay, let's do some algebra. I mean, just an algebra, high school algebra. Forget about linear algebra. Okay, so let's do this. Okay, so let me try to represent this in the following form. Okay, I'm sorry, you ignore this parenthesis here. Okay, all right. Now, what I'm trying to do, can anybody guess what I'm trying to do? Anyone? Can you guess what I'm trying to do? Nobody? I'm trying to complete a square. Okay. So the first term is fine. The second term is 2b by a xy. So what I need is 4b square by, not 4, sorry, really sorry, just b square by a square times y square. I need to add this so that I complete a square. But since I added an extra term, I need to subtract this as well. B square by a square, y square. And then I had another y square from before, c by a square. Okay, all right. Now, you should not have any trouble in recognizing that the first 3 terms within this parenthesis form a perfect square, isn't it? So I can write this as x plus b by a y whole square. Okay, all right. Now think about this. I know that a is greater than 0, right? And that's a condition for the parabola facing up. Okay, I know that a is greater than 0, and this guy is greater than or equal to 0, right? It can't be negative, correct? Okay, so now I'm left with this second guy, which is what? C by a y square minus b square by a square, right? So would you agree with me that I can write this as AC minus b square by a square, the whole thing times y square. Okay. Now, your y squared. So what I want to know is that in order for this quadratic form to stay positive, okay, positive or greater than 0, right? What do we need to have on the right? Now, I already know that this guy is greater than or equal to 0, but this can also be, the first term can also be 0, right? So the positivity of the second term will ensure that the positivity of the entire expression in general, right? So I have no problem with A, right? Y square is also positive. So my everything depends on AC minus B square, isn't it? Okay. Now, where does this AC minus B square come from? I think Rahul Saxena already told me, right? This AC minus B square is nothing but the determinant of this matrix A, isn't it? Right? So this AC minus B square needs to be positive. Okay? So that your entire expression, the quadratic form, remains positive or 0. Okay? All right, remains positive. And if it remains positive, there is a condition, there is a theorem in calculus that says that if your quadratic form is positive, then you ensure that the function that you are optimizing has a local minimum. Okay, all right. So how does it relate to the matrix structure? It actually goes right back to the structure of the matrix, right? And this is one thing that you should notice is that this matrix is symmetric, right? You notice that, correct? Okay, and this matrix also needs to be positive definite so that your corresponding quadratic form is positive. Okay, so what is positive definiteness of a matrix imply? The positive definiteness of a matrix imply that its corresponding eigenvalues are also positive. Okay, all right. So let me write that down. So a symmetric positive definite matrix implies that your X transpose AX has to be greater than 0. Okay, all right. So do you see how a matrix structure represents geometry and actually solves a multivariate optimization problem? Okay, all right. So now, how does this imply, how does this condition imply that the corresponding eigenvalues are positive? Anyone? Because a symmetric positive definite matrix by definition has to satisfy this, that X transpose A is greater than 0, which is a quadratic form, right? And such conditions of the quadratic form ensures that the quadratic form has a local minimum. Okay, all right. So you see how calculus is getting connected to linear algebra, right? Okay, now what I'm saying is that what was my original claim, that eigenvalues of a symmetric positive definite matrix are positive. Okay, now what is this AX, guys? Anybody? You can speak. You already know an eigenvalue representation, right? Hello, it's easy. AX is nothing but lambda x, isn't it? From your eigenvalue, eigenvector equation that you know. So I can replace this by X transpose lambda x and maintain the condition for positivity of the quadratic form. Now, what is lambda? Lambda is a scalar, right? An eigenvalue is always a number. So you can pull it out, you can write it in any order, doesn't matter. So you have lambda times X transpose x. That is also 0, right? Now, what is X transpose x? It's nothing but the norm of x, or the norm of the vector, right? This is nothing but the length of a vector, right? You know that the length of a vector cannot be negative, and therefore this lambdas has to be positive. This is immensely useful in singular value decomposition, because eventually what you are getting is that you have that singularity matrix or the singular matrix, right? Where its singular values are actually square root of the eigenvalues of the original matrix. Okay, so the eigenvalues if the eigenvalues are positive, eigenvalues cannot be positive or negative, because then when you take the square root, you have a problem, right? If a negative eigenvalue, take the square root, you get an imaginary number. So the positivity of the eigenvalue ensures that your singular values are also positive. Okay, and therefore you arrange your concepts, the concepts that you are trying to learn, the strength of the concepts. In this case, what kind of movie genres are more popular? You need those numbers to be positive as well. And that's the reason you need this particular property, that if you have to deal with somehow, when you decompose the original term document matrix, the middle guy, the middle matrix, has to be a symmetric positive definite matrix, so that you can extract the singular values and create a spectrum of the singular values which are all positive, okay, in a descending order. And based on the values of those singular values, or the magnitude of the singular values, you figure out which genre is the strongest and which genre is slightly weaker, so on and so forth. Okay, all right. Okay, so these are just the foundation stones for understanding why a singular value decomposition works the way it works. Okay, so we have mentioned two properties here: orthogonal matrices preserve angles and lengths, and eigenvalues of a symmetric positive definite matrix are real and positive. Okay, and I will finish by writing this, and this is the next step to understanding a singular value decomposition, is that every real matrix, and it doesn't have to be a square matrix, any real matrix, okay, or a corresponding linear transformation, can be decomposed into the following. Okay, all right, where Q is an orthogonal matrix or a linear transformation, and this sigma is an upper triangular matrix. Okay, all right, and this pretty much forms the foundation of singular value decomposition. We need to talk about this more. Please also remember that we need to invoke some other properties, which is a set of orthogonal vectors are linearly independent. We haven't yet talked about it or proved it. We will do that in the evening class, right? But I think before I forget, I just export this to and I will upload these to the whiteboard folder in the Google Classroom. Okay, after the end of the class. All right. Okay. Let's go back. Yeah. Okay, so all right, guys. So you have any questions? Okay, why AC is greater than B square? It's because AC, if AC is greater than B square, then only you ensure that your quadratic form on the left, which is AX square plus 2BXY plus CY square, is positive. Because that positivity ensures that you have a local minimum. Okay. Clear? Okay. All right, guys. So I'll see you again today evening at 7 p.m. Okay.